Okay, welcome. So, what we're going to be covering today, it's going to be a shorter lecture. It's going to be on magnetism. And I want to discuss this. They're mostly just for for completeness sakes. We're not really going to have enough time to go into magnetism in any depth. A lot of this stuff would take quite a while to go over. So, what I want to do is give you a little bit of the history behind magnetism and what I think are sort of the three big takeaways from this, and then a little bit of elaboration on that. So I'll show you some of the equations, but we won't have any homework problems or test problems that are on any of this stuff. Just think about this as kind of just kind of some bonus material that you're not going to get tested on. Still worth paying attention to, though, of course. All right. Let's go ahead and share the notes. Okay. So what we have here, first thing I wanna do is I want to do the three big takeaways that I think are kind of the most important things. If you've only got, a short lecture to discuss it, um, the three big takeaways for magnetism are going to be as follows. The first one is that moving charges cause magnetic fields. Okay. Now, when we think about magnetic fields, that's kind of the effect that a magnet has, and we'll talk about what kinds of things a magnetic field affects, but that's basically what the idea there. So another way you can think about that statement is moving charges cause a magnetic effect. Okay. The second one is magnetic fields exert forces on moving charges. Okay. So the idea is that not only do magnetic fields moving charges cause magnetic fields, and I'll actually indicate under moving charges, I'll indicate just one thing that may or may not be clear. Current is included in this idea of moving charges. So um so that's worth keeping in mind. So not only does a current generate a magnetic field, but a current carrying wire would also feel a force from a magnetic field. Okay, so we'll get into that too. Now the third one is going to be the kind of the I think this is the most important one, but you do need a little bit of foundation with the other two before you could really dive into it to understand it. This is changing magnetic fields. Changing magnetic fields can generate currents. Okay. And ultimately, this is how electrical power generation works. So when you have a power plant to generate electricity, this is fundamentally what's going on. Okay. So that's kind of what's happening. Now, I do wanna go back to first of all, what I want to do is I just want to give you some notation. Um, B, this is the symbol for magnetic field. Mu naught, this is a constant that is relevant, comes up a lot. It's called the permeability of free space. We're not really going to go into what that is or why, really, even we're not really define it, but it does come up just, and it comes up in the context of magnetism, like the Coulomb's constant or the gravitational constant that comes up in electrostatics or in gravitational field. Now, the other thing that's worth talking about is physical magnets. How this is largely what is going this is largely how people observe magnetic effects, and this was an observable effect back to ancient Greece. Basically, in ancient Greece, there was a particular type of stone that they called lodestone, that they found that if you put this lodestone, I think there were some interesting things where if you spun the lodestone, it would fall towards the north more often than not. So if you spun it like a top, it would topple and be facing like in a north-south direction more often than any other direction. But so back to ancient Greece. But you can also put one of these on like a cork floating in water, and it would naturally pivot the cork so it would face north. So this was the kind of the first navigational compass. All right. Now, basically, what what these things are, these are materials. They're fundamentally, it's just a material that responds to a magnetic field. Now, it turns out that all materials do this to a certain extent, but it's only observable in very specific materials. So, for instance, that lodestone I was talking about happens to be an iron-rich rock. Now, we'll get to that in a minute, um, but it wasn't until people kind of discovered the connection between current and magnetism that eventually these magnetic materials were explained, and I'll get into why that's the case. But it was a guy by the name of Hans Christian Ørsted. Hans Christian Ørsted. He was the one that discovered a current carrying wire would deflect the needle of a magnetic compass. Okay. So this was rather an impressive discovery for 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 just understanding the connection between electricity and magnetism. It wasn't entirely clear that that was the case. So I talked before about how you could charge things up with amber. You could do that. The ancients could do this, but there was they didn't really observe any connection between magnets like this lodestone and things you charged up with amber. There wasn't really a connection there. This is largely because they couldn't generate currents. They didn't have the ability to do that. So when people were able to generate electrical current, that is moving charge, they could see the connection. So that's what was going on there. Now, again, there's a little bit to this, but this kind of goes to that first point. One, that currents, and again, by currents, we can also think about that as a moving charge. Moving charges, like in a vacuum, will generate magnetic fields as well. But this kind of goes to that first point. Now, the interesting thing about this is that, well, actually, well, before we do that, we'll jump on to the Biot-Savart law. What the Biot-Savart law is, this is just the law that mathematically states that relationship. And I'll just give you the kind of a simple one. It's that your magnetic field is equal to mu naught I over 2 pi r. Now, ultimately, this is actually a simplification to take into account that current needs to flow basically in a line. If you could have like a little point space of current, then that would look much more similar. That would actually be an inverse square law. And that's actually how the Biot-Savart law is formulated. It's formulated as an integral, but there are no point items of current. Like current always at least exists in a line. So it's not like a charge where you can have a point charge localized in one, at one point in space. So that's kind of one of the things that's going on. But this is basically the B field from a current carrying wire. B field from a current carrying wire. Now, it's a little difficult to draw B fields, but if we had a current going in this direction, I, the B field would actually form a circle around it. So what you would have is you would have the magnetic fields forming around in circles around this wire. Now, basically, they would be, so again, the B fields form circles, and it's a little bit different than what we saw with electric fields, where they would, point from positive charges to negative charges. These B fields, did that one the wrong way, but these B fields are actually making circles. Okay. Now, to find the direction of the B field, you have to use something called the right-hand rule. I'm not going to get into that now, but the whole point is that the B field forms a circle around the wire. All right. So that is a rather that is kind of a unique thing. Now ultimately the reason this happened, that Hans Christian Ørsted saw this, what he would actually see is he would see that if his deflection would only work if the needle was above or below above or below the wire. If it was above, it deflected the opposite direction than it would below. And part of the reason for that is the fact that these magnetic fields are going around in circles. But in any event, that's kind of just a little bit of elaboration on that first idea. Now, it turns out this also leads to what's going on in magnetic materials. Now, basically what you have is you have a B field generated by the atomic structure. And I'm going to try and get into that a little bit, but not a whole lot. I'm just going to start with kind of a simple atom. It's just a simple model of an atom. So you have plus Q in your nucleus. And what you have instead, you don't have your electrons embedded there, and we know this isn't quite how it works, but the way we can think about this is that you have your electron and it's going around the nucleus like this. Now, fundamentally, what this is, it's a quantum mechanical effect, but we can kind of think about it just for simplicity as is like an orbiting. So this orbital, and I'll just put in parentheses, orbiting electron generates a B field. Okay, so what this means is that anytime you have an electron orbiting like this, you will have a B field. And in the context of materials, we tend to call this a magnetic moment. I'm not going to get into that too much. But the point is that every atom with an orbiting electron like this has a magnetic moment. Now, there are some complications with it because there are very interesting effects that go on in materials. So first of all, if you remember chemistry, you can have paired or unpaired electrons. If they're paired, it turns out that largely the magnetic moment cancels. Now, what's interesting about that is that doesn't necessarily mean that there's no response to magnetic fields, but it does make it a little bit more complicated. The other issue that comes up with this is that the atoms are not all aligned with one another. Okay, so you don't get a really strong magnetic effect from a material unless all the magnetic moments align. And this is what actually happens in things called ferromagnetic materials. So in ferromagnetic materials, these are the things that permanent magnets are made out of. And it's really limited to a few elements, iron, nickel, and cobalt. And basically with these, and sometimes you can introduce some impurities to increase the ferromagnetic effect. But basically what's going on is that magnetic moments tend to align in clumps called domains. Okay, so if you ever hear information about ferromagnetic materials, you probably hear this term domain. And basically all that's all these magnetic moments from, so basically in this case, what we'd have our B field that look kind of like that. But what you'd have all these magnetic moments from these materials aligning together. Like basically it affects its neighbor. Now, you will also have multiple domains. It's not like the entire material is a single domain. And the domains, like in normal, in just average iron, you do get these domains, but the domains, they counteract the effect of one another because they are not all aligned with one another. Now, what you can do is if you heating a ferromagnetic material, and then you put it in a B field, what this will cause is it will cause many domains to point in the same direction. And once this happens, then you get then what you have, this thing is now a permanent magnet, okay? And basically, you just need more domains to be pointing in one direction. You just need the average direction of the domain to be pointing in permanent magnet. You just, geez, okay, I got to erase. Permanent, permanent magnet. You just need the domains to be lining up on average in one direction for the thing to be a permanent magnet. And you do this by first heating it. Basically what heating it does is it breaks down the barriers between the domains. The domains kind of form naturally. It's a thermodynamic consequence of what's going on. But if you if you expose a magnetic field while it's hot, and then allow the domains to reform, what will happen is that more of the domains will be pointing in a single direction, and this thing will, on average, have its own magnetic field because you've lined up so many of these magnetic moments in the same direction on average. Okay, so this is what you ultimately get for in a ferromagnetic material. It's how permanent magnets arise. Now, you may also have heard the term, if not, it's fine, but I'll just introduce these: paramagnetic and diamagnetic. Now, paramagnetic materials, they're somewhat similar to ferromagnetic, except they don't have that domain element. Now, what this means is it means that you're never really going to get a hugely strong effect, like even if you heat it, because they don't form domains. They'll just kind of naturally tend to flip. Like it's this tendency to form magnetic domains that keeps the permanent magnetism. Without that tendency, paramagnetic materials they don't have a strong magnetic effect when exposed to magnetic fields, and two, they don't have much of a they won't form permanent magnets. But you still do get weakly attracted to magnetic fields. Okay, or I guess I say in magnetic fields, weakly attracted in magnetic fields. Basically, a magnetic field will generate a weakly attractive force. In diamagnets, it's kind of interesting. These are the ones where you have paired electrons, so you don't have any of these net magnetic moments. However, and this is way beyond the scope, when you expose these to a magnetic field, you basically get an opposing magnetic field because basically none of these electrons want to change their shape. So in order to do that, they generate an opposing magnetic field. And ultimately what this results in is a weakly repulsive force. So weakly repulsive in magnetic fields. And it's kind of interesting. These two phenomena, all of these phenomena can be observed. They're the simplest magnetic phenomena to be observed, but they're some of the most complicated to explain. It's much easier to do the physics of magnets in magnetic fields from current carrying wires than it is to observe the magnetic effects of materials. But that was kind of the one that I wanted to indicate there. Okay, so for the second one, 4.2, this is magnetic fields exert forces on moving charges. And the idea is that not only do moving charges generate their own magnetic fields, but if they go into something else's magnetic field, they'll experience a force. Okay, so the second one, this is the magnetic force law. It's a little bit simpler. But I do just want to indicate something. So what you have is you have FB, your magnetic force. That's equal to your magnetic field times your charge times the velocity of that charge times the sine of the angle between the two. Now, what this means, if theta equals 0, F sub B equals 0. So the interesting thing about this is that for magnetic forces, you actually get less force the more aligned the velocity of the charge is with the magnetic field. Really, what you want in order to get the most force, you want theta to be 90. So you want the velocity to be actually perpendicular to the magnetic field. Now, another thing about this is F sub B is always perpendicular to V. Now, to just kind of give you a sense of how this works, what these X's represent, they represent a magnetic field into the board. So field into board, or into page, I should say. So used to doing this in the classroom, I usually say into the board, but really it's just into the page. So really, if I'm the magnetic field is kind of it's in the direction. So as I'm looking down at this, it would be down into the page. Then what you could have is if you had a positive charge plus Q with a velocity V going this way. Basically what you would have, hold on, I need to remember it. Yeah, what you would have is you would have a force in this direction. So basically your magnetic field would turn this particle. And it turns out that what actually happens is the thing goes in a circle, assuming it never leaves the magnetic field. If it leaves the magnetic field stops affecting it. But basically, the magnetic field will end up turning it. It won't speed it up or slow it down. So you can generate a lot of circular motion with magnetic fields, and this is kind of how it connects to some of the things we talked about earlier. But again, like I said, we're not really gonna have time to do that. I just kind of wanted you to see this connection here. That magnetic fields can exert forces on moving charges. Now, they also exert forces on moving current carrying wires. So B fields exert forces on current carrying wires. Okay, so the idea here is what you would have is you would have your magnetic force on a current carrying wire is equal to B I, and then the length of that wire, sine theta. Now, the way you can think about that is the time component associated with the velocity in the first equation got shoved into the current. So basically, you need to have a certain length of wire inside this magnetic field, but the length of the wire in the magnetic field has a force exerted on it. So I'll just indicate that L is the length of wire in B field. All right. So the way this one would work is basically we have something like this, and then we have our wire going like so, carrying current in this direction. Basically, what you're gonna have forces on the wire in like so. So you'll have your magnetic forces being exerted, in this case, in the upward direction. Now, in depend like this is it's a little less clear what happens here because this wire is it could be rigid or it could be fixed like it, so you might just get this wire moving upward. Ultimately, we're not really going to have time, but the fact that you can get this kind of force from magnetic fields on current carrying wires. This is one of the ways that magnetic levitation works. If you can generate currents in both spots, one current can generate the magnetic field, the other current can be repelled by that magnetic field. And so you can have magnetic levitation in that way. But again, like I say, a little beyond the scope of what we have time for. But basically, that's how this would work. Now, to discuss the last one, that changing B fields generate currents. And this is, like I was saying, how electrical power generation works. Now, the idea is basically that instead of having a moving charge, what you're doing is you're having a moving B field. Now, it can't that's a little it's a little less clear what that means in the context of a field rather than an object. So the way we often will, instead of saying a moving B field, we'll say a changing B field. Because like the B field that really what we mean by changing B field is if we have a permanent magnet, we move that around, that changes the B field, and doing that can generate current. Now what you need, it turns out, I'll just try and do a simple demo of this, or not a demo, but a simple diagram of this. So if you had a load and you had a loop with no voltage source. Well, what you could do to get current to start flowing through this is you could take a bar magnet, so this would be north and south, and you could take a bar magnet and put it through the loop. Now, it has to be moving. As soon as you bring it to stationary, it stops working. But if you move it through the loop, basically what happens is you will generate a current in this loop, and you can see the current, you can see the current driving through the load. Like if it's a light bulb, you can get the light bulb to light up. It's a voltmeter, you can measure voltage, or an ammeter, you measure an amperage there. Okay, so basically this is the way you generate EMF. Now it relies on a concept that I'm not really going to go into it in any great depth, but it relies on this concept of the symbol is capital Phi B sub B, and what it is magnetic flux. And what magnetic flux is, basically it's weighting the strength of the magnetic field by the area that the magnetic field is going through. So it's sort of a measure of the strength of the magnetic field. In that if you take a bunch of magnetic field and you concentrate it all into a single area, you have a much more, it's not necessarily a stronger field, but it's like a more dense field, if that makes any sense. So you can think about this, the flux as being like a measure of the density of the field, the concentration of the field in a particular area. And it turns out that it's actually this flux quantity, if that changes. So your EMF, and remember that's your EMF is just a voltage. So the voltage generated is equal to the change in magnetic flux divided by change in time. Okay, and really that's a derivative. For other reasons, that should also actually be a negative. But really this is fundamentally what's going on. Okay. And again, this is how electricity is generated. It doesn't matter if it's a thermal power plant, a hydroelectric plant, wind turbine. If you're taking mechanical energy and turning into electricity, that's fundamentally what you're doing. You're taking like a permanent magnet and forcing it to go, generally repeatedly in circular motion, forcing it to go through these loops of current. And that is what's ultimately generating, or sorry, these loops of wire, which ultimately generates the current. Okay. This is why, if you've ever heard that windmills require magnets, they do, because that is fundamentally how you take motion and convert it into electricity. So I hope this just gave you a little bit of a primer. Again, don't worry about memorizing these equations. I'm not going to give you any problems on them. But hopefully that was useful. Thank you for joining me today, and I will see you in the next class.